Hello and welcome back. Today I want to continue talking about mechanical switches and methods to protect them from misuse by trying out some possible circuit configurations, but also looking at how such protection elements need to be chosen. So if you're curious, then keep watching. Last time I looked at the various methods that are commonly used to protect switches from exposure to overvoltage and overcurrent. But how do you choose between one method and another? Well, one criteria is price. An RC network is usually cheaper than a semiconductor like a transient voltage suppressor. And probably you want the smallest possible component that will ensure the necessary functionality. There is no point in using a 10 ampere rated component when a 1 ampere one is sufficient. So it's easy to overdimension something just to be on the safe side. But that's not good engineering. So to start things off today, I will be shortly looking at the case of capacitive loads. So as a basic example, I created a circuit that has a 100 volt supply and the load has a 100 microfarad capacitive reactive component. If we run the circuit as is, we can see that during the turn on phase, the current through the switch reaches infinite values. So this is because there's no series resistance and we're using ideal components. Now, if we want to limit this current to, say, 1 ampere, we need to add in a resistor that can achieve this current limit when the load capacitor is discharged. So when the voltage on it is 0 volts and you get the 100 volts supplied. And this will occur when we add in a 100 ohm resistor. And well, if we do this and we recheck the current, we can see clearly our 1 ampere current peaks. Now, with this setup, the power getting dissipated on the resistor when the load is active is around 800 milliwatts. And it's not really difficult to find a resistor that can handle this sort of continuous power. But what's important to keep in mind is that the resistor will have a huge power peak getting dissipated on it during the turn-on transient, which in this case is about 100 watts. Now, an 100 watt resistor is physically really big, but you don't really need a resistor that can handle 100 watts continuous. You need something that can handle 100 watts just for a few milliseconds. Now, I found a couple really interesting application notes from Vishay, a major resistor manufacturer, talking about pulse handling resistors. I'll leave links to both of these documents in the description, of course. But there are a few key elements I want to highlight. So first of all, the pulse handling capability is dependent on the resistor technology. Your SMD thick film resistors are the least suited, whereas a thin film resistor is better suited. Main reason being the way in which the resistive material is printed, so just how homogeneous it is. And if you want something even better, you have your wire wound resistors, which are made from a solid piece of wire. So this sort of component will have far better peak power handling capabilities. The last thing to observe is that you can dissipate more power the shorter the pulse length is, but this is allowed only until a certain point. So here we have an example graph from a MELF type of resistor, where the peak pulse power increases by about 100 times as the pulse length decreases, but at some point even shorter pulses will have the same power rating. So you can't dissipate more than a certain amount of power, regardless of time, without risking to destroy the component. And the exact behavior will of course be component dependent. And well, a good datasheet will highlight this. Other than resistors, it's also common to use NTC type thermistors. Here, it's again important to mention that the same general problem exists. The thermistor needs to withstand the peak power that will get dissipated on it. So you have two big categories: the temperature measurement NTC, built for accuracy and small currents, and the inrush limiting NTC, which has an accent put on pulse handling. So make sure you choose the right type of component for your specific application. So to highlight one of the problems that you can run into with capacitive loads, I prepared this basic experiment in which I'm using my high voltage supply set to 100 volts to supply a 100 microfarad capacitor through my old current probe. Now, the power supply is limited to about 150 to 200 milliamps of output current. So do we really need any sort of current limitation? Well, let's turn on the power supply and see what happens. So when the voltage gets activated, when it's connected to the capacitor, we see a small spike. So if we zoom in a bit, we see that the current jumps to quite a high value. We have about 2.5 amperes here, so it's 500 milliamperes per division, after which the current drops to a smaller value, and the voltage then slowly increases. So what we're seeing here is that at the first moment when the switch is turned on, the output capacitor of the power supply discharges directly into the load capacitor through any sort of internal limiting resistors, after which the current limit kicks in. So on this rising slope, we see the current limit in action, the 150 to 200 milliamps, but at the very first moment, we are getting 2.5 amperes, which is not current limited. So even when working with current limited power supplies, it's important to keep in mind that the output capacitors, once charged, will discharge with no current limit unless you add something in. So this is one case where an extra current limiting circuitry might still be needed. Let's now continue by looking at the case of an inductive load. This could be something like a relay, a transformer, a motor, or just a long wire. For the sake of simplicity and ease of modeling, I'll be using a 15 ohm resistor in series with a 100 microhenry inductor, and driving these from a 10 volt supply through a relay. So I build the circuit on a small board, and as a switch relay, I'm using a 5 ampere 250 volt AC rated component. So this is switching the 10 volts into our load. And to be able to observe what's going on, I have my high voltage probe measuring the voltage that is present on the load. So the voltage that the contacts are seeing are the supply 10 volts minus whatever the probe is measuring. So if we run the circuit as is and just make a single capture, we can see that during both transitions of our switch we are getting some high voltage spikes. So this is because the contacts are bouncing, they don't have a clean turn on, turn off transition. And the spikes are in the 276 in this case, but they go up to around 300 something volts. So at some point the internal contacts will be arcing, and anyway the voltage will be limited by the various parasitic capacitances occurring in the circuit. So these high voltage spikes are what we want to prevent today. So let's look at some methods how. Today I will check the following. On the semiconductor side, a basic diode and a transient voltage suppressor, and on the passive side, a basic resistor, a varistor, and an RC network. First thing to use is a basic diode. When the switch will turn off, the current running through the inductor will close back through the diode. This is also sometimes called a flywheel diode. Now, for the sake of this initial simulation, I will be using a diode which has a generic model. So when we run the simulation, we can see that the voltage on the load does go to negative values, but these are clamped by the diode, and thus the voltage that the switch sees only briefly exceeds the supply voltage. Now, if we check the current running through the diode, during its conduction, the current reaches a value of around 600 to 700 milliamps. So the exact value will of course depend on the load. So what practical diode should we choose to conduct the current during this turn-off phase? Well, one common component found in various schematics online is the 1N4000 series diode. This is quite an old component, but it's easily accessible, and it's rated for an average forward current of 1 ampere. So it will do the job. But is it necessary? Could I use something rated for smaller currents and still be safe? Well, this is the datasheet for the 1N4148 diode and, well, similar ones. This is another common component which is only rated for an average forward current of 200 milliamps, which is well below the 800 milliamps of peak current occurring in our circuit. But could we still use it? Well, similar to resistors, in the particular use case of short current pulses that occur on relatively rare occasion, when choosing components, you don't care about the average forward current, but rather about the peak forward current. So if we look at this specification, we can see that this diode can withstand for a period of 1 second up to 1 ampere, which is more than enough for what we need. Our simulation predicts that the inductor will be completely discharged in about 17 microseconds, with the peak current of 800 milliamps. So this diode should do. Now if we look at the same specification for the previous diode, we can see that it can handle 45 amperes if the pulse is less than 1 millisecond. So this diode would have been extremely overdimensioned for our task. So I added the 1N4148 diode in parallel with our load, and if we turn on our switch, we can again see negative voltages at both turn on and turn off because of the switch bouncing, but the minimal voltage is limited to about minus 1.7 volts. So this is perfectly normal for this diode when a current of around 700-800 milliamps is running through it. So if we let the circuit run for a while, well, nothing really breaks. So this works just fine. Anyway, in datasheets of components designed to actually take some amount of power, so not really small signal diodes, you will get proper graphs highlighting their pulse handling capabilities. So how much power and current they can handle for short periods of time. So that way you can make sure that the component will work correctly in a long-term use case. Next, I want to look at two common transient clamping components, a varistor and a transient voltage suppressor. I will be using some components I already had around, so they were not specifically chosen for this application. But regardless, there are a few things we can learn about them and how they behave. So first, I added into the circuit a 14 volt AC rated or 18 volt DC rated varistor. So if we turn on the circuit and we have a look at how this is behaving, well, we can see our spikes are being clamped, but the clamping voltage is about minus 32 volts. Not really the 18 volts that the component is rated for. And if we zoom in a bit, we can also see that there's a very clear ringing appearing. So is there something wrong with the component or with the measurement? Well, for the use case of protecting against transients, the varistor needs to be chosen with a lot of care. So for the component I'm using, I found this datasheet, but these are general behaviors of this type of component. First of all, the actual voltage at which a specific current is allowed to pass has quite a bit of tolerance. In this case, it's plus minus 10%. Second, the current to voltage characteristic graph shows that the varistor is always conducting some amount of current. So it's a very small value at its rated voltage, so in the order of 10-50 microamps, and then it slowly increases as the varistor is exposed to higher and higher voltages. So if we take the 14 volt rated component, at around 14 volts it does have 10 to the minus 5 amperes, which is 10 microamps. This will be the maximum current at this voltage, and then if we go check the 1 ampere point, the maximum voltage at which this current will be achieved is somewhere in the 40 to 45 volt range. So it's perfectly normal for the 14 volt varistor to not clamp 14 volts. The exact clamping point will be current dependent. Now, the other thing that we observed was ringing. This usually indicates that the inductive load is resonating with some sort of capacitance, and if we go back through the datasheet, we can find that our component has almost 10 nanofarads of parallel capacitance. And if we run the numbers, an 100 microhenry inductor will resonate with a 10 nanofarad capacitor at 159 kHz. Our measured value was 161 kHz. So when searching for varistors, you don't just care about clamping voltage and pulse handling capability, you might also be impacted by this parallel capacitance. So now I added into the circuit a 11 volt rated transient voltage suppressor. And if we run the circuit like this, we can see that in almost every single cycle, the minimum voltage is clamped at 14 volts. So it's not exactly 11 volt, but it's very close to the rated voltage of the TVS. So although this sort of diode is usually more expensive than a varistor, the TVS is far more precise and predictable in its behavior, and at the same time can be built to have lower junction capacitance. So when the exact clamping voltage threshold is critical, like in low voltage systems, or when you need very low added parallel capacitance, like when protecting communication lines, the TVS type of diode is usually better suited than a varistor as a protection element. Next, we can look at resistor and resistor capacitor networks, but first in the simulator though. So starting off with the resistor only network, The resistor can be designed to give a specific peak reverse voltage if we know the current running through the load, and the downside of this method is the constant power draw that will occur. Final thing to keep in mind is that the resistor needs to be able to handle the peak power that gets dissipated during the turn-off phase. So if we want a low permanent power, we get a large resistor value, but this will mean that we get large peak reverse voltages and large peak power dissipations. So if we run the simulation with a 240 ohm resistor, we can see that this is giving us peak negative voltages of minus 160, the permanent added power is around 400 milliwatts, and the peak power is in the 100 to 110 watts. But this gets dissipated for only a few tens or hundreds of nanoseconds. So if we try with a resistor in parallel with the load, we see that it is clamping at around 120 something volts, so various different values depending on the pulse. But this is one of those cases where just because it works doesn't mean that it's reliable. So right now I'm using a resistor that is not specifically designed to handle high power pulses, so it will work, but it's not very sure for how long. So to make sure that your circuit runs reliably, you need to make sure that you choose the right type of component. Now, by going with resistor-capacitor networks, we kind of fixed both issues. There is no permanent DC load, DC current cannot pass through the capacitor, and at the same time we can use smaller resistors, which will ensure smaller reverse voltages. And with smaller voltages, we will get smaller peak power levels. Now, when choosing the exact components, there are a few things to keep in mind. Depending on how you look at it, there will always be some amount of voltage dropping on the capacitor, so this can be calculated quite easily if we neglect the various resistances present in the circuit. And if you use very small resistor values, you could end up with a circuit that oscillates. So if this oscillation is a problem, there is a certain formula you can use to determine the damping factor of the series RLC circuit that was created. So anyway, if we run these two circuits, one that has a 47 nanofarad capacitor and 4.7 ohm resistor, and one that has a 47 nanofarad capacitor and a 47 ohm resistor, and we zoom into them, we can see that both of them are giving roughly the same negative voltage, 21 volts, but the circuit with the 4.7 ohm resistor ends up oscillating. If we look at the power dissipations, the larger value resistor, so R5, has a peak power level of 21 watts, whereas the 4.7 ohm resistor has a peak value of around 2 watts. But because less power gets dissipated on it, the power is dissipated over a longer period of time, and while the inductor gets discharged slower. So if we start off with the RC network with 50 ohms and 47 nanofarads, and we run the circuit, so we can see our clamping action at around 23 volts, so similar to what the simulation was telling us. And if we zoom in enough, we can see that there's no oscillation going on. So there's a bit of a hip here, but it's not oscillating. Now if we try out different combination, say the 4.7 ohms and 47 nanofarads, and we rerun the same test. So first of all, we can see the oscillation has appeared, so as predicted by the simulation, but now our minimum voltage is about minus 31 volts. So here the simulation was telling us something different. And it's important to remember that this is a ceramic capacitor, most likely of X7 R-type or something similar. So when you expose this type of capacitor to high voltages, the value won't stay constant. So just to make sure if the problem is with the capacitor or with the simulation, I have this other RC network where I have the same 4.7 ohm resistor, but this time the 47 nanofarad capacitor is of film type. So this will definitely maintain its value. If we try this component, well, we can see the ringing again, and we can see our minimum voltage at minus 19.6. So when your capacitor in your RC network ends up seeing large voltage variations, it's important to make sure that the capacitor actually keeps its value during the voltage pulse if you want the predictable behavior to occur. So finally, coming back to the practical circuit I was talking about last time, the one with the broken switches, how did I end up fixing it? Well, for the voltage spike, I used a basic diode, the normal operation current of the relay is below 200 milliamps, so I went with a 1N4148, and I could have used a lower current rated diode, but I just didn't have one. And for the inrush current, well, I added a permanent 5-watt resistor, which I think is of carbon film type. And the relay then clamps both the switch and this resistor, disconnecting them from the circuit. So this component only sees a large current and peak power during turn on. And well, the circuit has been working without any issue for the past year or so. So these were not some complex additions, but they make the difference between a reliable and a non-functional circuit. In the end, protecting the contacts of mechanical switches can be done in multiple ways. And since the switching action is occurring relatively rarely, the exact implementation method can have quite a bit of variation in its behavior without actually impacting functionality. This situation is a bit different with semiconductor switches, where the switching can occur far more often. But that is a topic for another time. For now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be updated to all my latest videos, and see you next time. Bye bye.